Welcome in Dark Core. We often picture space as a cold, silent void, a place where nothing exists. But the reality is far more complex. Even just above Earth's atmosphere, space is filled with fragments, particles, and streams of solar wind. And the farther we travel from the edge of our solar system to the space between galaxies, the more we find that what looks empty is actually full of structure and activity. In this video, we'll explore what really fills space, why it matters, and how future missions will help us understand it even better. Let's get started. The discovery: space is never truly empty. The myth of empty space breaks down almost as soon as we leave Earth. At the International Space Station, orbiting roughly 400 kilometers above the surface, we're already beyond nearly all of Earth's atmosphere. But the environment outside isn't a perfect vacuum. It's filled with micrometeoroids, flecks of paint, and other fragments racing through orbit. What we see on the ground as shooting stars, astronauts hear as faint impacts on the station's hull. That's how crowded low Earth orbit really is. Move beyond this thin shell of debris and we meet the solar wind, a constant stream of charged particles flowing outward from the sun. This flow shapes a vast protective bubble around our solar system called the heliosphere. The wind isn't uniform. Solar storms and fluctuations can damage satellites, disrupt instruments, and threaten astronauts far from Earth. Monitoring these conditions has become a critical part of space operations. Farther out lies the helipause, where the solar wind loses strength and encounters the surrounding galactic environment. This is the region where Voyager 1 and Voyager 2 are now. For the first time, we're directly measuring the space between stars, and it's far from empty. The interstellar medium, a diffuse mixture of gas, dust, and magnetic fields, fills the gaps between stars. Though incredibly thin compared to anything on Earth, this material shapes how radiation travels, how stars form, and how galaxies evolve. From low Earth orbit to the interstellar frontier, every step outward reveals something: particles, fields, or radiation where we once imagined nothing at all. What fills the cosmic void? The interstellar medium might seem negligible, but its influence is enormous. It's mostly hydrogen with helium, dust grains, heavier elements, cosmic rays, and tangled magnetic fields. While only a few atoms may exist in each cubic centimeter, those few shape the behavior of light, star formation, and galactic evolution. One of the most visible effects is interstellar reddening when light from distant stars is scattered and absorbed by gas and dust. Astronomers must correct for this to see the universe clearly. Without understanding these interactions, we'd misread everything from stellar properties to galaxy shapes. The same material that dims starlight also builds stars. Dense pockets of gas and dust collapse under gravity, becoming stellar nurseries. Over time, stars form, live, and die, releasing matter back into the medium, which seeds new generations of stars and planets. Space isn't just occupied, it's constantly recycling itself. Our solar system currently drifts through the local bubble, a low-density region likely carved out by supernovae millions of years ago. This bubble influences how the heliosphere interacts with the galaxy, effectively shaping the boundary between solar and interstellar space. But the structure of space goes beyond our galaxy. The intergalactic medium, once thought to be almost empty, contains diffuse gas stretched across vast distances. This material connects galaxies through massive filaments, forming the cosmic web, the largest structure in the universe. These filaments feed galaxies with fresh gas, enabling them to grow and form new stars. Even cosmic voids, the spaces between these filaments, aren't truly empty. They contain faint traces of hydrogen, weak magnetic fields, and the lingering glow of the cosmic microwave background, the oldest light in the universe. Modern telescopes and probes are mapping these faint structures with increasing precision. Instruments like the James Webb Space Telescope, Hubble Space Telescope, and Euclid reveal how even the faintest gas leaves its signature on light. Closer to home, missions like Interstellar Boundary Explorer, IBEX, and Interstellar Mapping and Acceleration Probe, IMAP, are mapping the shape of the heliosphere and its interaction with the interstellar medium. What emerges is a clear picture: the spaces between stars and galaxies are not voids but active environments. Invisible matter, radiation, and energy fill the darkness, shaping everything we observe. Implications and what comes next. Understanding what fills space isn't just academic, it has real practical consequences for exploration and science. For spacecraft, even a microscopic particle can be dangerous at high velocity. A grain of dust traveling at tens of kilometers per second can pierce metal. That's why long-range missions must account for micrometeoroid and particle shielding, not just radiation. Interstellar particles also influence communication. Solar activity and charged plasma can distort radio signals, especially for spacecraft operating far from Earth. Future human and robotic missions to Mars and beyond will need systems that can adapt to and mitigate these effects. For astronomers, the interstellar and intergalactic media act as both obstacle and resource. They absorb and scatter light, making distant objects harder to study. But their spectral fingerprints reveal the universe's history, recording how stars lived and died, how galaxies formed, and how the universe evolved over billions of years. These gases also help refine our models of large-scale cosmic structure. The cosmic web, once purely theoretical, is now being mapped through its faint imprints on light. This structure shows how gravity, dark matter, and baryonic matter interact to shape the universe. Future missions promise to push this understanding even further. IMAP will provide high-resolution data on how the heliosphere meets the interstellar medium. Telescopes like JWST and Euclid are already detecting faint gas in intergalactic space. Together, they'll help us probe the limits of how sparse, and yet still structured, space can be. Studying what fills space tells us how stars are born, how galaxies grow, and how the universe sustains itself. The closer we look, the clearer it becomes. The idea of a true void doesn't hold up. Space isn't empty. It's full of matter, energy, and history. Even the darkest regions shape how the universe evolves. The void, it turns out, is anything but. Thanks for watching Dark Core.